Welcome. Today I'm going to talk to you guys about something that I refer to often in this class and that we will refer to over the course of the year pretty often, and that is ideal conditions. Ideal conditions are conditions in which we simplify things by ignoring certain influences. Now, if you do things right, if you do your experimentation the right way, you should be able to minimize the effects of things like friction and air resistance or drag. And then you can approximate this thing called ideal conditions, as if there were no friction or there was no air resistance. If that's the case, then it makes your math and your analysis a lot easier, and so that's why we do it. So that's what we're going to talk about today. This is the 15th video. It's on ideal conditions. Okay, so the first thing I want you to think about, if you can, is putting your hands together and moving them back and forth. Now, anything that's moving has kinetic energy. So if you're moving your hand this way, it's got kinetic energy, and then you move it back down the other way, it's got kinetic energy, and so on. So you're using the energy in your body that's stored from the food that you eat to create kinetic energy in your muscles, in your hands. Then what you may notice is that if you do that enough, the skin in the space between your two hands, the place where one hand rubs up against the other, you start to notice that it warms up. And the reality is that there is this thing called friction, and friction takes kinetic energy and it steals it from objects and then converts it into thermal energy. And it does that on the microscopic scale in something that looks like this. So if you want to think really close up on a certain small area of the surfaces between one hand and the other. Okay, so let's say one hand, here's your hand over here, this is hand. Let's say that's your left hand, and then that's your right hand. Okay, and the surface between for your left hand looks something like this. And the surface for your right hand looks something like this. And so you can see, I'm going to go ahead and sketch that out so you can see more clearly what I'm talking about here. There we go. So one hand then is moving in one direction, and the other hand is moving in the opposite direction. And so these surfaces are rubbing up against each other. So this hand has kinetic energy, and this hand has kinetic energy. But the problem is that some of that kinetic energy has to be used to overcome the places where ridges and valleys in two surfaces kind of get locked in place. So you can imagine, as you see this little bump right here, kind of coincides with this little depression right there. We have another little bump right here, and there's a little valley right there, right, a depression right there. And so some of the kinetic energy that you put into the system goes into breaking the connection between those two surfaces. And so as a result, what ends up happening is the particles that are in this surface and the particles that are in this surface, because of the collision between the two surfaces, they end up vibrating more and more often. You could say more quickly if you want, or with a greater frequency is probably the best way to say it. And so their increased vibration is what we feel as heat. And so we end up increasing the thermal energy, which you may remember from chemistry is signified with a Q right there. So the thermal energy goes up every time there's a collision between these microscopic hills and valleys. And as a result, the kinetic energy for the system goes down. As there's more and more of these collisions between the hills and valleys, you get more and more heat built up and less available kinetic energy for motion. And that's why objects will stop. So if you have let's say a surface and a wooden block, and you slide that wooden block across the surface, it will not travel forever. The reason for this is because the interaction between the surface of the table and the surface of the wooden block takes kinetic energy away from the system and converts it into thermal energy. And so if you measured the temperature of the wooden block before and after you slid it, you would notice that the wooden block has actually increased its temperature because it has more heat. Now we're going to talk more about these topics when we get into thermodynamics, but for right now it should be pretty simple to you. If you want to heat up your hands, what do? You rub them together. Why? Because you're using one kind of energy to convert to another kind of energy. It's also why objects don't move forever in a straight line, like they probably should, as we'll find out in the next video. Hopefully that makes sense. So the other question then is, why don't objects, some objects that have a very large surface area, why don't they fall straight down like other objects? Here's an example. I have a feather. So a feather looks like this. Okay, like so. You get the idea. There we go. And you have a metal block, like so. If you drop them both, the metal block will fall straight towards the ground and hit much quicker than the feather. The feather might float to this side, and then float back to that side, and then float back to this side, and then float back to that side, and then finally hit. What's the difference between the two? Is it gravity that's causing the problem? The answer is no. It's actually the fact that all objects, and I'm going to draw this, I'm going to draw this horizontally, but it's the exact same idea. All objects, like for example the front of a car, okay, have to travel through a medium, and this medium is the particles of air. And so if we could see those particles of air, they might look like this, right? All these air particles all surrounding there you go. Oops. I get too close, they connect the dots there. So those air particles are in front of and are surrounding the car. But as the car tries to push forward through them, some of the energy of the car, remember it has kinetic energy, some of the energy has to be used to push these particles out of the way. And so as a result, it loses kinetic energy. And there is, if you want to think about it this way, with reference to our next video, there is a force that is applied backwards on the car because the car has to push all of those little particles of air aside. The air particles push back on the car. So the same thing happens here. The air particles are actually pushing upward on the feather. They push upward on the feather. Now the feather has a very small mass for a very large surface area. So the effect of that little push, and it is just a tiny little push, is very obvious. So you can see that's the cause of the floating downward of the feather. However, on the metal block, you have a push upward that's very small compared to the mass of the metal block. And the mass of the metal block is much bigger, and the surface area is much smaller. And so that little push does not affect its motion towards the ground very much. In fact, it's not very observable at all unless you have very accurate and very precise measurement tools. Whereas with the feather, it's very accurate. If you're able to take out the air that's in a system, like for example in a room, and then dropped these two, they would fall at the same rate and hit the ground at the same time because there's nothing pushing up to cause them to slow down. Now, why do I bring that stuff up? Well, because I'm going to start to talk about this idea, and I want to make sure that you know what I'm talking about when I get there, and that is the idea that we call ideal conditions. Ideal conditions are something that comes up often, and it's very simple. Ideal conditions, we assume that there's no friction between two objects that are moving past each other, and we assume that there's no air resistance or If you prefer the term drag, you can go ahead and use that as well. For vehicles, usually air resistance is called drag. So those two together make up the fact that we have ideal conditions. Do we ever actually have ideal conditions? No, because we don't ever have a situation in which we have no friction. We can pull all the air out of a system and have no air resistance, so that works out okay. But if two objects are in contact with each other, they are going to have friction, and so we can't ever get rid of this for real. But we can minimize both of those to an extent that we can ignore them. If we can minimize them enough, we say that they are negligible, which is kind of a weird word, and I only really see it anymore in physics textbooks. So I want to bring this up to you. Negligible. Boy, I hope I spelled that right. There we go. Negligible. So friction is negligible and air resistance is negligible. What do I mean by that? I mean that their effects are so small that we can safely ignore them and still get a very accurate answer for our measurements. So that's it. That's the idea. So part of the trick, though, with this is that you have to be able to be smart about how you set up your experiment so that you can ignore friction and air resistance. Many times people try, and if they're not smart about how they do it, they really have too much friction or too much air resistance, and that causes problems in their results. Okay. With that, I want to thank you guys for watching. Don't forget to do those note sheets and to write those interesting question forms. We're going to talk about this here in the next couple of days, so please make sure that you've got it. Also, ideal conditions comes up from now until the end of the school year, so it's definitely one of those things that you want to make sure that you understand. It's pretty simple though, right? No friction, no air resistance. Not that they're not there, they're just small enough that we can ignore them. Okay, thanks for watching. Have a great day.